Hey, Harshad,
Yeah, can you hear me?
I can hear you, but I can't. It has put me on some hot IEEE wings of fire or something
Yeah,
like
yeah, yeah, that's my daughter's Zoom account. So her
that.
favorite book has come up there. Yeah, no, no.
Okay, okay.
Um, but I can't start my video um,
Can
because
you?
the host has stopped it. Yeah, only one of us can.
Only one of us can do it. Okay. Uh,
But let
so
me share my screen. I think
yeah.
that. Oh, but host has disabled participant screen sharing, so I can't share screen.
Uh, I think I can fix that.
Thank you.
But- So the other session is still going on. That's why the chair hasn't joined.
Ah,
But I will fix those things for you guys.
okay. And right now I'm trying to see from this screen how to get rid of
Oh,
that weird
actually,
background.
I think Kshitij, you can you are the host because I think you started earlier than me. So
Uh-huh.
what you can do is you can transfer the host to me. I will set those settings and give it back to you.
Okay. How do so I just stop my video? Is that
No,
what
no,
will
no.
do it?
If you go to my name, there is a button with more,
Yeah.
and you can just make him a host.
Make a host. Okay. Yes.
Okay, great. Thanks. Let me fix that for you. Okay, I fixed the screen share. Whoever wants to share the screen should be able to.
Okay, I'm
Okay.
gonna start sharing the screen. Let me know
Yeah.
if it can be seen.
And
Yeah.
one more question is what's a good way to for me to get rid of this IEEE background and just put a blank or dark background?
Okay, let me see 1 second. Let me fix one more thing. I think right now, maybe just a second. So
So I have to give you the control, right? Again.
no, I think I still have a control. Let me second. Okay. So I think Arshad, you can share your video too now if you want to, if you desire to. So
Oh, okay. Let me see. Yeah, just a
and
second.
also I want to enable chat for everybody so that we can have more interaction. Uh,
I'm not terribly
Okay.
familiar with Zoom, so yeah.
So for you, right, if you go to Zoom, like preferences, or if you click on the video button, start video button, there is an option to choose a, virtual background.
Oh yeah, I can see that. Choose virtual background, right? And I can just pick none. Okay, good.
Yeah. Okay.
So that's good. And one more question I have is how do I stop the screen from occupying the entire thing? Right now it's occupying the entire screen. Oh,
Mm,
okay. Now it went back to normal.
okay.
My screen has gone blank. The Zoom part, I can't see what I'm sharing or not.
Yeah,
Uh,
you're not sharing anything right now.
yeah, you're not sharing anything.
No, because the Zoom window won't let me do anything. My
So
screen has gone blank.
are you on a web interface or app?
No, no, I have an app. Okay, now it came back. Just give me a second. I think I'll be able to fix this.
Okay.
Yeah.
So probably what's happening is you have somewhere green. That's why you are seeing some background on yourself. So if you don't like that, okay, that's probably something else.
But my screen is now sharing on another.
Oh, good. This time I can see you also. That's wonderful. So we are both on.
No, I'm trying to see if I can.
Hey Dave, I was just helping out Zoom stuff. So
Good, yeah. We went over a couple minutes in the last one.
okay.
Um, Did you give them sharing permission?
Yeah, they have every permission. I'll make you the host so that if need be, you can do something.
Great.
Right now, you are
Can
an
can you
expert by now.
see my screen?
Yes. Yes,
Okay.
Harshad.
Now,
Hey, and
hopefully, I don't touch anything.
yeah,
It stays.
and so we now just stay here until like whenever the thing starts, and we are okay. It's already 3:35. So
Yes,
let
it
us know.
is.
Yeah, so let us know when to start.
Yeah, sounds good. Let me just give, it looks like we're recording. Let me give a quick introduction. Thanks everyone for attending. This is our last tutorial for the day for track 2. We're going to hear more about microservices, in particular the map and zoom performance methodology from two great computer scientists. First is Harshad Suni. He's a performance engineer at the data center and AI group with a deep technical expertise in system software, memory, and CPU architectures. He specializes in performance monitoring, software optimization, and tool development with a focus in the cloud domain, of course. Harshad joined Intel in 2008 after completing his undergraduate degree in electrical and telecommunications from College of Engineering and Technology in Pune, India. And he has an MS in electrical and computer engineering from UC Boulder. Everyone calls him Doshi because he has the most incredibly difficult first name to pronounce, at least for me, but I'll give it an attempt. Kshitij Doshi.
Very good, thank you.
Is that pretty close?
Yeah,
that's the first time I've attempted it out loud.
That's good.
Yeah, Doshi, everyone calls him Doshi, works at Intel in the data center and AI group as well, where he focuses on performance optimization of workloads and cloud instances. He obtained his undergraduate degree in electrical engineering from IIT Mumbai in 1982 and his MS and PhD degrees in electrical and computer engineering from Rice University in 1985 and 89, respectively. His research interests span distributed systems, memory and storage architectures, and resource management. So again, I'll remind folks, we're taking questions in the Slack channel. I'll put the name in the chat. And with that, please take it away. I assume it's Harshad is starting.
Doshi.
I will start, and then Harshad will take over
Excellent.
at some point. Thank you,
Excellent.
David, and thank you, David. Greetings to everybody, and welcome. I am Doshi, and with me is my colleague Harshad Sane. We are excited to share our experiences today with you in dissecting into performance of microservices-based applications. In these solutions, we have loose coupling among fine-grained services which communicate with lightweight protocols, and such loose coupling reduces dependencies, and this speeds up developing and deploying new features. And so while that means high programmer productivity, it also means more moving parts which evolve independently. So when the whole solution does not meet some objective, the difficulty is in figuring out why that is happening. And sorry, I've got a Slack thing. Okay. So when something does not meet a desired performance objective, the difficulty is in figuring out why that is happening and also what to do about it. So today, from our work with customers, we have some lessons to share, and let's start by laying out some reasons for this journey. So slide 2. So what we want to do is discuss various reasons why optimizing microservices requires systems thinking. And by that, we mean going beyond classic software tuning. Certainly, classic software tuning is part of performance engineering, but we have to go beyond that. And in order to explain this, we look at a list of high-level issues in microservices performance engineering that are on the top right. And what we will do is, for the next few slides, we will look at each of the first-order factors for each of those those high-level issues which are on the top right. On this slide, we'll consider the first-order issues that are arising from the microservices architecture software pattern itself. So the first of this is referring to the fact that even though these finer-grained services are structurally independent, there is a a fairly large amount of need for them to converse now and then through API interfaces and to send data and events. So performance can be lost if these interchanges become very chatty. Second thing is that unlike a monolithic application where components invoke process local interfaces, now we have remote API calls, which add overheads like serializing and going through the OS. And then what happens is frequently one microservice has to wait for some other. And that means that where the waiting is occurring is separate from where the causes for the waiting are building up. And so that separates causes from observed effects. So we have this split observability. Network overheads arise, so does congestion, and so that takes up time and resources. And very often encryption gets added in the mix when we are talking about network interactions. And then the other thing that happens is that the at what time and at what priority different critical resources get assigned to say one microservice A do not take into account the fact that there may be dependency chains. Many of them are dynamic. They are data flow chains. Other dependencies which are ordering based, right? So all those dependencies occur, and yet the resource allocation is oblivious to that. So so we have we have those kinds of resource fragmentation issues. So a performance effect then is hard to link to its causes, particularly when these causes and their effects arise dynamically. And often these cause to effect chains are long, and they may even be circular. So those are all some of the complicating factors of performance engineering arising directly from the pattern itself. Now let's go to the to hardware issues, which are on the next slide. Now, no, for not many years ago, it was sufficient to collect simple profiles, hardware event counts, code hotspots, and pretty quickly you zeroed in on where the performance issues are occurring. But over the years, processors have been getting deeper and wider. So today we have hundreds of threads with potential for hundreds of instructions per thread to be in flight. And so when this instruction level parallelism begins to fall off, simply getting event telemetry is not enough in order to locate something, or even simply locating code hotspots doesn't tell you why those no, why we are suffering from a loss of instruction level parallelism. The other thing that happens is that, excuse me, with a large number of threads in execution, sometimes it's the memory capacity, memory throughput, or cache bandwidth, right? Those are all starting to emerge as the underlying roofline or performance limiting factors. And so what happens is that at that point, even if you were to go and engineer the software to work right in order to remove some of these stalls, thread level parallelism still suffers. So having gotten rid of some stalls here and there doesn't really improve, because there is something else that limits the performance. So what happens overall in the first bullet is that we have many different overlaps that determine performance outcomes, not just in one microservice, but across the overlapped execution of multiple microservices. The second thing that happens is within the first bullet, we talk about speculation. The high instruction level parallelism depends critically on speculating and executing out of order. And when that does not work, many partial executions have to be quashed and reissued. With microservices now, once again, the problem is one of, which one of these stalls, right, is really critical to the overall application performance. The second bullet here refers to the fact that modern machines also have very deep data access pipelines for their cache hierarchies, with additional steps for operations like prefetching, prediction, etc. So when hiccups occur in these pipelines, back pressure develops in code pipelines as well, because of all the data flow dependencies like traffic backing up at a toll booth. The third bullet refers to the fact that we have a complex mix of frequency points and sleep states for good performance per watt and for effective thermal control in modern architectures. So transitions between these operating points, frequency points, as well as sleep states can cause overheads. Then we have the next bullet talking about the fact that we have a significant amount of increase in instruction grained fixed function acceleration in order to achieve high throughputs for very complex workloads like AI, post quantum crypto, and so on. So typically these compound instructions have variable latencies, and even though they are out of order, trying to figure out just based on simple profiling, where to pinpoint the occurrence of stalls, and what are the precise data flow dependencies that are leading to those stalls, particularly because in source code a lot of the variables, right, are mapped at runtime to their pointer values. Uh, uh, what you just considered are all the hardware factors. So we consider the software factors, we consider hardware factors. Now let's go to the next slide where we'll talk about some of the shifts that arise because of different performance objectives of different solutions. So what happens is we have performance goals which also influence the analysis, and in addition to the hardware and software effects, we have to inquire into what is happening with respect to a specific performance goal. Now, classic performance objectives have been typically about maximizing throughput or efficiency or minimizing response time, or sometimes minimizing one or the other constrained by some other metric or some other service quality objective. And so effectively what happens is that they boil down to, in the case of monolithic applications, reducing some critical bottlenecks, right, where a critical resource like CPU time, power, or bandwidth is being lost. So it's a constraint optimization problem. With microservices, we have the opposite issue, in that the microservices typically are purpose focused, they are specially designed, they are heavily tuned for their specific objective. And so when they are in compound operation working with one another, figuring out where the bottlenecks are occurring becomes an issue, and how to assign resources correctly, how to schedule things at the right time becomes a kind of a multivariable constraint optimization problem. And then when we look at the fact that modern deployments have continuously evolving performance objectives, each of the ingredients also have their own independently evolving objectives. That means that we often have things going on in tension. So let's take the second bullet where we talk about an uh, 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 example of improving response time. What can happen here is that you may have an inference microservice that may need to maximize a performance per watt or a performance per unit bandwidth objective, which is what it's optimized for, and it is, let's say, feeding or is being driven by a relational database microservice which needs to achieve the highest possible cache efficiency. Now these two goals can be in conflict if the solution architectures are trying to do two different things at the same time. And so one solution might be, okay, let's move them apart, let's put them on on network separated machines. Well, now you have introduced new barriers to meeting performance objectives, because now network bandwidth, network congestion applies, high availability issues arise. So these performance objectives being diverse also complicates the search for optimum solutions. And we'll now go to the next slide where we'll talk about, in particular, end-to-end tail latencies control, which is a dominating factor in today's deployments. And this happens because a lot of our modern applications are um, uh, uh, evidencing AI-enabled real-time mediation of computation, um, be it in a transportation system, in a social network, a business process, etc. And in these real-time situations, right, the end-to-end latency control is important because it directly affects the user experience of many of these applications. Further, in many of these applications, under the user perceived interaction, there are thousands, maybe even tens of thousands of microservice to microservice interactions coming into play. And these also have, therefore, their own tight latency cutoffs. Otherwise, the overall solution would fail to meet. And particularly for these underlying machine-to-machine automated operations, the high nine operation for tail latencies can be much more stringent. Instead of one or two, instead of two nines, right? They may require four nines, five nines worth of tail latency control. One example we can consider here is mid-transaction analytics. Like, you're trying to perform an e-payment transaction, and right in the middle of that transaction, right, a fraud analysis has to occur. Another good example of this would be ad insertion, where the business objective is to maximize the click-through rate, and yet a second business objective is to ensure that that users are not turned off, that their video doesn't become jittery, and their content consumption experience is not is not unfriendly. Now, the funny thing about all these extremal latencies is that they add up. So variations in latencies add up instead of being statistically amortized at 99.99 percentile points. So let's sum up some of these four factors that we've just walked through in the next slide, and what that means from a performance engineering standpoint. And from a performance engineering with microservices standpoint, we would argue that it requires a system of systems approach in place of one that takes the view that we just have to get all the ingredients right and put all the optimized parts together. Zeroing in on causes of effects becomes challenging. Um, that is because they may not be closely related in space or time. Something that started happening, let's say, millisecond ago, may have its ramifications occurring for the next tens of milliseconds. Similarly, effects may not be linear, where you might say 50% of my compute time is going into this microservice. Let me double its throughput by giving it more resources. You are unlikely to see necessarily a 25% increase in performance, because the hotspots might shift somewhere else, and the effects may be non-local, right? So the fact that you made something faster may only improve the total solution performance marginally. So to sum it up, right, we need a disciplined performance analysis and optimization methodology in which the focus is on the interrelation of the parts to each other and to the whole system. And this is where it's somewhat of an irony, because loose coupling, which is designed for high programmer productivity, essentially paradoxically creates tighter coupling in the performance feedback effects that permeate throughout the system. So with that, right, we believe we have made a case that a disciplined methodology is required, and we'll shift to the main body of the tutorial. So this is going to be our flow of topics today. We'll start with a few problem signatures that we see commonly in our optimization work with our customers, with our developers. Then we will list a number of common causes of performance bottlenecks or suboptimal performance which come to surface when we investigate these various end user visible effects. In looking at performance from a systems engineering lens, we have to find a way to divide and conquer, and that's what the total recipe is about, the map and zoom recipe. And the whole idea is divide and conquer, triage, peel the onion, so to speak, and so that we have an overall blueprint in place for how we want to go after various perplexing performance issues. After we have described the methodology at a very high level, we will have a 7-step recipe. The intention is that these recipe steps are followed mostly in order, but we also expect that there will be frequent retracements after you've identified and solved one problem. Then you go back to the top of the recipe and begin again in order to reestablish whether a new problem signature is developed. So when we have covered the 7-step methodology, we'll essentially be at the end of the tutorial, we'll be wrapping up, and we'll be spending more time on additional questions. In the meantime, right, if you can help us keep the keep the conversation interactive by asking questions on Slack, that'd be wonderful. So let me transition to the next slide, where we talk about these simplified, 3 simplified problems. These are narratives that are illustrative of some of the customer cases that we get. We have intentionally tried to simplify them so that they are not, they don't bring with them all of the other confusing material with them. So the first one is showing a knee in a scaling curve, where the horizontal axis is the total number of cores that are allocated to a collection of microservices. As more cores are given, scaling begins to fall off, or the return per additional amount of CPU starts to fall off. Now, there can be many possible factors. This is a very common pattern that we see. For example, on the hardware side, network or memory capacity may not be enough, cache capacity may not be enough, software choke points may be in the form of concurrency limiters, or uneven distribution of work among threads. Right, those things can happen. We've talked about weights that happen between different microservices. So a lot of different things can be, it can be causing these kinds of knees in a scaling curve. And so some of the other things that we will describe, right, would be good ways of inquiring into those things. Next, in problem 2, we look at a problem of choppy latencies, where the situation prior to the problem being solved is on the left, where we have multiple microservices that are running. On the vertical axis is their performance metric, say in the form of latencies. On the horizontal axis is simply the flow of time. And at some point, what happens is that we have, we solved the problem, right, by figuring out what was going on. And when we applied the solution, right, all of that choppiness and latencies went away. Now, what could be happening that could be causing this? Well, imagine that you looked at the underlying event signatures, and you saw, oh, uh, I have high L1 cache misses, I have high L2 cache misses, but I don't have too many LLC cache misses. Further, most of the time, most of my services seem to be waiting on something. So what could be going on here? It turns out that one of the classic ways that this kind of situation can develop is a problem that we often refer to as fault sharing, where two variables that are semantically unrelated, logically unrelated, but they just happen to unfortunately fall on the same cache line, where the high amount of write traffic rate against one of the variables causes that cache line to keep bouncing between cores, because others are reading that cache line for the other variable. Usually the solution to this is very simple. It's to make sure that the structures are properly padded, especially where we expect these kinds of hotspots. The problem number 3 scenario, right, is describing two microservices. Let's call them M1 and M2. Here, what happens is that again, on the horizontal axis, we have got time. The vertical axis is showing two different measures, a latency measure and a throughput measure. Some other service starts up, and what is shown here is are these measures for M1, for one of the microservices, which is the principal microservice, its throughput drops off and its latency spikes. Even and you look at M2 is running very infrequently. It's not a particularly compute intensive service, and yet it causes so much amount of hiccup in M1's performance. Um, Turns out to be a fairly simple factor here. M1 happens to be a service that say it depends upon very low latency transactional writing to be finished, so that micro transactions can be retired very quickly. It really requires very high core and turbo frequencies. Um, M2 is not very well tuned. It bounces around. It's a best effort service, and yet it ends up getting vector ISA exercise sufficiently that it pulls down those core frequencies that M1 is depending on. Was there a question, Harshad? Or
No.
okay, so next we look at some of the common causes of these kinds of situations, and there is a reason for listing some of the common causes that seem to arise often, and that is to reduce the total number of diagnosis challenges by ruling in or ruling out a few of the high running causes that seem to occur in very many places, so that the total number of really complex problems that we have to investigate, right, reduces. We can also achieve some amount of divide and conquer. So the first set of common causes tends to be around the growing footprints and the numbers of software entities that are typically shared by modern large platforms. What happens is that we have over time a large number of software agents, each with their own independent dynamic memory access footprints. They have got to be supported against a relatively slowly increasing amount of last level cache and processor caches in the machine. And so that leads to overheads, noisy neighbor effects, and latency excursions. The second bullet is referring to the fact that we see that in recent times there has been a growth in the internal concurrencies of many applications, where either it will be standard kernel thread supported concurrencies, or even library concurrencies supported on top of user level threads. And what happens here is that you end up with fine-grained sharing of caches, and that can cause both actual sharing type of contention as well as fault sharing type of contention that we saw in the previous slide. The third bullet here refers to speculation effects, where what has happened over time is that execution pipelines have become deeper, and as they become deeper, they become more vulnerable to bad speculation. And at the same time, usages have become more crowded with use of dynamic types, interpretation, indirect branching, high levels of indirection in variable access, right? So all of these things have a tendency to increase the likelihood that either branch prediction or address speculation, right, goes awry. And when that happens, right, you get bad speculation. Power management is talked about in the fourth bullet, and it's referring to the fact that in recent times, right, sleeping quickly as soon as there is an opportunity, or shifting quickly to a low power mode, has become very important with the urgency around sustainability and efficiency. But at times, right, this cuts against keeping tail latencies in check, because the worst case things start to come to the fore. We have the loose coupling delays, where you have sometimes excessive signaling and coordination delays, and that can happen if somebody has done their microservices factoring with too much fine-grained factoring, right? So they've ended up creating extremely interactive, not very efficient types of messaging interactions. We talked about fragmented resource management earlier, and today that's happening a lot because across the many different agents, there's a tendency to allocate and manage the life cycle of various resources, cache various resources, and so on. So effectively, the finite number of hardware and sometimes even software resources end up getting fragmented, and so we get inferior overall solution level performance. Those are some of these causes, and knowing that we should expect one of these causes enumerated here allows us to design experiments in order to rule these things in or out. And while there may be exceptions to the rule, a lot of optimization problems or opportunities can be speeded up by doing such triage. So with that, let me transition the speaking control to Harshad. Um, I don't know if I have to do something specific in order to make Harshad the host.
I hope I'm audible.
Oh, yes, you are audible.
Okay, thank you, Doshi. Again, feel free to ask questions. Now we'll actually go into some of the implementation of the methodology that we are talking about. The top part of David, the top part of the screen is kind of the Zoom window is covering it. I'm just trying to figure out if I should. I don't want to stop sharing, but I'll just continue. I think I have the content. Yeah, go ahead.
It looks okay to me.
Yeah, it's looking perfectly fine, Harshad.
Right, the application on my side gives me the control window that covers up the title, and so that's fine.
I know what you mean. I've seen that before. It's unfortunate. I honestly don't know how to move it either. It must be a way, but
no worries. Okay, so let's jump into the map and zoom methodology. So I mean, let's face it, microservices are going to be complex, right? Those who have been used to doing performance debug and looking for software optimizations in monoliths, there has been a process and methodology, and you're kind of looking at generally one stack. And as you move towards microservices, it's just so distributed that it's hard to say where do you want to start and what your problem might be, because as a user or a customer, you're looking at your end goal, which might be a perceived latency or throughput, but it can the problem or a high latency or a dip into throughput can manifest in so many different places, because we have made it easy for us to develop because of microservices, but it made it harder to debug now. So we need to establish a very disciplined approach to evaluating such performance problems, right? Firstly, if I go through some of these points, firstly, we need to understand what is the environment that we are working in. So create an established baseline as to say, hey, these are the health of my components, whether it's software or hardware, and this is basically they are healthy enough that I'm going to now start doing some amount of profiling or understanding what the chatter is about. Secondly, we want to create a map, which means that we want to establish the KPIs that we are talking about, which is latency, throughput, but then establish them in a way that we can attribute them across the microservice and have a visual of what that architecture looks like. And then once we have a visual of that, and I'm going to give examples of what that looks like in the next few slides, we want to actually be able to zoom into some of these such that we can then detect anomalies and unexpected behaviors, and then be able to iterate through them, right? So imagine it almost follows a tree-like structure where you start at the high level, you have this whole Death Star bench-like view, or Death Star-like view, I'm sorry, and then you figure out you have a few components that are outliers, and then you're able to zoom into each component, and then within that component, you might have multiple layers, and then it's a matter of peeling the onion. And once you find, let's say, a solution on one of them, you apply the solution, and then you'll find that your problem shifts elsewhere. It may not be an exaggerated problem as what you solved previously, but it's more of a whack-a-mole kind of problem, right? And then you basically iterate this methodology. So I'm going to talk about the 7-step journey. As Doshi mentioned, this is typically follows a particular order. But sometimes, and there are very, very few times that we like to directly jump to say number 4 or number 5. But ideally, if you are simply doing a performance experiment, it is highly recommended, and it's a tried and tested performance methodology that helps figuring out opportunities for software optimizations or detecting, issues that you'd like to debug. So it starts with a health check, then we move on to a component breakdown, which is where we do the map part of the map and zoom. And then we move into more deeper dives, such as performance characterization, doing software profiling. And then the next 3 are more of a different set of optimizations, right? Number 5 talks specifically to addressing non-scaling parts of your application, whereas number 6 says how can we take all of this that we talked about and we basically automate it and make it much easier for ourselves, because deep diving into every issue into this complex phenomena of microservices is not going to be easy. And we also talk about security overhead, because that forms a very, very important pillar, as well as, although as important as it is, it brings about performance overheads, and how can we, first of all, identify and then mitigate them. Okay, so let's go start into each one of these, and within each one of this 7-step journey, I'm going to introduce some tools. Some of them may be things that are in theory, some of them are proof of concepts at Intel, or some of them might be tools that are in the open source, and I'll refer to them, but feel free to connect later or ask questions. So let's start with health check.
And just right now, I think I would point out that that we have additional slides at the end that actually have pointers to some of the tools.
Yes, yes, thank you. There'll be glossary and references for the same. Okay, so let's start with health check. And even prior to microservices, this has been a very important part of standard methods of performance evaluation, where for example, you would want to know what processor you're running on. You would want to know what Linux version you're running on. These very, very simple things. But if you could bring them all under one umbrella, and especially for a complex microservice or multiple applications talking to each other, it makes it very, very simple, and it makes it a very quick method of evaluating your baseline. Not only that, when we actually move into some actual performance excavation, we'll find out that we'll need to refer back to some of these health checks. And you'll see why as I use some tools to kind of show the same. The reason we want to spend more time on health checks, although it seems very basic, is that we work with a lot of customers, right? Being in the positions and companies that we are, and we find out that 50% or more of cases actually are resolved at the place where environment variables are wrong, or certain knobs are not set correctly. And these are really large percentages. So it's very important to spend some time here. Although with tools, we have made it very easy to get past this very quickly. Some of the examples that we'll see is hardware features like BIOS, firmware configurations, simple information about the CPU, the OS, the kernel, and then along with that, we'll also have micro benchmarking. Now, micro benchmarking is important, but ideally it should be done on an idle system, because it is going to establish your limits, and it is going to establish what is maximum possible on that system, be it memory bandwidth on the system, or CPU utilization, or network, or storage, right? But knowing these limits helps you, because when you actually are doing some performance evaluation, you would know that you are not you're violating any of these limits, right? And you are in a healthy condition. Similarly applies for the software part of the health check, where you would want to see libraries, utilities, processes. All of them are also, not you're within the limits and bounds of what you're running. So with that, let me give you an example of a health check tool that will dump some of these things. Number one, let's look at what are the things, hardware details that are going to be done. This is an HTML view of the same, and you would see things like what is the baseboard, what is the product name, what is the BIOS version, what's the release date. Many a times you're on really older BIOSes. What is the power characteristics of this platform? How much power can it sustain? What is the frequency governor? And frequency driver. These are very important ones, because you'll see by default, when a system comes up, at least on the Intel P state driver, it's very common to see it come up in the power save mode. Like Doshi mentioned, for sustainability and efficiency, we always want to start in a power save mode. But that may not be the best mode for certain situations where latency is very critical and the wake up of CPUs is very critical. Let's imagine you're running a gaming application and there are bots fighting each other, and suddenly you've killed one bot, but then the other bot pops up. So there are multiple threads that are being spawned, and it will so happen that the other bot, while coming up, and it may or may not be visible, but you might observe jitter because the thread took a lot of time after it went back into sleep, and it's respawning the same process. Even the data may be cached, or sometimes it may be flushed if it's gone in a deep power state. But you want to be able to reduce that jitter. So there are a number of tunables there, and it's good to know and have control over some of these. Right. Similarly, on the right hand side of this, you have got. I'm assuming you can see my pointer here, but you can see the CPU model, the architecture, which is very important, and its limits. Right. How many CPUs does it have? Whether things like hyper-threading are enabled, prefetchers is enabled, turbo is enabled. These are hardware knobs that are settable. Some of them even through the OS, but they let you know, what is the maximum frequency this processor can go to, as an example, right? For example, here it's 3.1 gigahertz when all cores are active. When we'll go deeper dive and into profiling, we'll be able to see these numbers because we'll be collecting this information. And when we collect this information, we might see everything's running at 2.8. And we might just go past that, and we'll direct, let's say, you find an issue and you start doing code profiling. But if your processor is running for some reason at a much lower frequency, how much of a code profiling one may do, we are not still mitigating the fact that there is a hardware issue at play. And it may not be a hardware issue, it could be because of a software issue. So it's important to have this level of detail established. Now let's go through an example of one of these, right? Let's imagine we collected this information. This is the second view in hardware, where you might see, hey, what does my DIMM population look like? And this is an example of an actual DIMM population we have collected by a customer in production, right? The DIMMs were literally haphazardly, although haphazard in a way, but you can see there is some form of schema to it, where 2 DIMMs are populated, then 1 on the second slot, then 1 on the first slot. But what happens with this is the processor expects one to have a symmetrical layout, and works best when the channels, the slots in the DIMMs, and the DIMM population is more symmetric and even. And that leads to bandwidth and latency phenomena. So after visualizing this, we changed the DIMM population. You can see that 32 gig DIMMs have been replaced by 16, which makes it still having the enough memory, but then all the DIMMs are symmetrically populated. What that does is, and this chart has been generated with a tool called MLC, or Memory Latency Checker, which is available externally. The resources will point to it. But what this tool does is it incrementally increases the pressure of the amount of reads or writes, or the bandwidth pressure in memory, and it sees the response of the system. So the response is seen on the y-axis, which is latency, excuse me. And the injection is on the x-axis, which is in terms of bandwidth. So as normally seen by any system, not just computers, you would see a hockey stick-like curve, right? It's not necessarily linear. Initially, you will see great performance from the system, where it is flattened in the beginning. So until we reach 25, 50, 100, 125 gig of bandwidth or 100 gig of bandwidth, it's doing great, this blue line. And then you see it suddenly spike up. So the latency has gone up, right? So what you're going to experience is much higher latencies if you're within this operating region. Now, when the DIMM population was this way, this is exactly what we saw with this blue line. When the DIMM population was changed on the right-hand side with being more symmetric, now you can see the yellow line, right? Or the red line, rather. The yellow line is just a reference that Intel gives to say, hey, this is what, given this system, this is what it should look like. Now, just looking at these two lines, you can clearly state, hey, something's wrong in my system. Let me fix that first before going to my application. There are a lot of software issues that can also lead to this, but being able to plot something like this gives you an idea of what to expect in terms of memory latency and bandwidth from your application. Yeah. The third part of health check is a software side of things, right? One may want to look at what are the active processes that are executing, what is the CPU utilization, what is the memory footprint, also what are all the versions that we are dumping, right? You might have some GCC, glibc versions, Python, Java, so on and so forth. Look at this interesting place where, of course, at some point someone installed a Python 2.7, you got a Python 3.6, you may have a Python 3.8. Now, because of the way an application may be written, or because of environmental variables, or because of layering, one application may execute from one Python and other might execute some other version. And you will see a huge discrepancy because of the underlying libraries that it utilizes or the way it has been designed. And one may see unexpected phenomena because of that. So it's important to capture the versioning information and the underlying libraries for the same. Right. Similarly, on the hardware side, it's important to know what are the capabilities of the processor, which are depicted by something called as an ISA, or the instruction set architecture. So what's shown over here on the right-hand side is there is AVX capabilities, there is vectorized advanced encryptions standards, there is AMX. There are different kind of instruction sets here, and the yes or no just says, hey, whether I'm able to make use of this on this architecture or not, right? On the memory side of things, you've got, what things have been utilized, typically what's being cached, huge pages have been used or not, whether NUMA balancing is enabled. So all of these are essentially useful to establish a health check or a baseline. Okay. Again, feel free to ask questions. I'm going to move on to the next one. Now, once we have completed a health check and we are sure that our health is good, we want to move on to something known as component breakdown. This is the place where we establish our map phenomena. Now, microservices in a mesh, they are just too complex, right? We don't know where to start. And one may find that there are choke points, but we don't know where that choke point may be coming from, because we are seeing the choke point from a point of an observer that my latency has a spike or my throughput has really gone down within certain hour of the day, but I don't know where to pinpoint it to. So we want to be able to map out such that we can focus on the next level of drill down, right? One may be able to do that by traditional instrumentation, such as doing Jaeger traces, right? But to do that, you would still want to know where do you want to instrument at, right? So we want to take that first step in doing that. So this is a precursor to performing a detailed analysis, which will be done in the zoom in process. But we really want to establish that first step. Okay. I hope this visual. Yeah.
Do you want to talk about the Jaeger overheads and why the EVPF, or you want to do
yes,
skip
I
that
think
later?
I think I'm going to skip that because that repeats later, and I'll talk about it there. Yes, thank you. The map process, as you can see, this, I have just clipped off a very small portion of one of the microservices that we were testing, and this is a tool in progress that's POC. But what it's capturing is it's capturing all the chatty environment. It's capturing all the services that are talking with each other in terms of TCP endpoints, and then it's creating this view of, for example, I don't know if you can see, OpenResty is talking to some text service, is talking to some unique ID service, and in turn is calling a compose service, and so on and so forth. But this map gives us an idea of what the microservice looks like, but also what's important are the arrows between them and the weights of the arrows, which can be depicted in terms of numbers or can be depicted in terms of color coding for those arrows. But overall, what you see is that this is a hairball of a mess, and we want to pick out, rather than picking where the problem is, we want to get rid of this mess, right? We want to simplify the problem. We want to really look at what's important. And that's essentially what the tool does. It is going to, and in this tool, what's being used is eBPF, which is Extended Berkeley Packet Filter, a very important technology in this domain, initially built for networking, but is used over here for performance analysis, is where it instruments dynamically information such as the data, the TCP chatter between different applications without even having to go into the data of the TCP packet. It's simply seeing who's talking to whom, how much data is being transferred, and how much time is being spent. And that is very important because it gives us this view of saying, this is our first step in performance analysis. Because now once I know this, I can start looking at OpenResty and user service. I wouldn't have to care about things on the right-hand side. I can say, okay, I think user service is where I'm spending more time. There's a lot of time being spent between these two services, and there's a lot of data being spent between them. Let me start digging into, and let me start applying the Zoom methodology, which is the second part of the map. So now once that we have created a map and we have created the red sections of the map, which tell me, hey, this is important, or this is where I want to focus on and get my data from, we want to start doing something known as performance characterization. Now there's in the computing world, there are the term profiling and characterization are intermixed and invariably used together, but I want to make it clear that characterization is very different from profiling. In the performance world, when we talk about characterization, we want to characterize the entity or the process or application and say, what does it look like? Is it a memory bound application? Is it a cache intensive application? Does it, if it's a database, is it going to be more IO intensive? At a high level, we want to characterize the application. But when we go into profiling, we want to go into parts of code, right? We want to get the instruction pointer and then go into parts of code. So we always like to start with characterization, yeah, because it gives us a one level above profiling. So modern processors include a lot of performance counters in something known as a performance monitoring unit, and there are hundreds and hundreds of such events, and they are related to the CPU architecture within, its caches, its TLBs, it's within the memory, the IO, the PCI subsystem, or the buses within the CPUs, and they collect all this information at runtime. And PMU drivers, very, very prominent drivers such as perf, can retrieve all this information at almost negligible overheads. So we want to use characterization using the PMU hardware to quickly identify where is my application bound, right? First. So that's what characterization is going to give you. So let's deep dive into what it looks like, right? An example of using perf to get a lot of this data, it could span across hundreds of counters, right? On the right-hand side, what you see is a typical general, pipeline of a processor. Now, if you just look at the arrows and these blocks, it's a very complex processor. It's out of order. It's pipeline. The pipeline is just growing over the years. And you can see that, the width of the pipeline based upon how many instructions you can issue, you can parallelly compute and then be able to fetch and retire, right? That's essentially what happens in a CPU engine. Although this is a very complex beast, we can actually narrow this down into different regions. We can say the part where instructions are fetched decoded can be calculated as the front end. The part where it is the events are the instructions are actually executed is your execution engine, and then the rest of it is backend where you go to your caches and your memory. Now the challenge is when an application is running, it is executing instruction essentially from a hardware point of view, right? Now, based on how it's executing instructions, where it's incurring its stalls, it will imprint a different signature on the processor itself and in this diagram. Now, the challenge is to decipher where in the processor, where are these stalls occurring? And all these events are related to the structures that you're seeing on the right-hand side. However, you can see this blue line as a perfstat command, and I've given a very, very simple version of it. Typically, you would have hundreds of events here, right? Which then relate to metrics. How do you use this? So we've developed tools, and you would see how we can high level this information, right? So let me introduce a tool called as Perspect. It is a tool that you can find in the open source. It's a tool written by Intel. It's a wrapper, but what it does is it allows you to take all these hundreds of events that we showed, and it allows you to high level them into this tree-like structure, which you see on the right-hand side. So you don't have to deal with these raw events. It's more human readable. And then it creates this tree-like structure with different levels, right? At the level 1, you may see something as front-end bound or bad speculation, retiring, or back-end bound. These are the only 4 things that generally can happen as instruction move through the pipeline. Now, within each one of them, there could be various reasons why something is front-end bound. Now, let's imagine a Python application, and runtime notorious to be known to be front-end bound. You might be spending 40 or 50% in front-end bound, whereas a database application might be 40 or 50% back-end bound. And within each, you can actually, the counter information can then specify, hey, within front-end bound, I found you are spending most of your time in branch mispredict, right? And then we can actually go into code and move into the next level of profiling and then figure out where that is happening, right? Similarly, if you're memory bound, it could either be core bound, or you could be cache bound, or you could actually be DRAM bound. And with the help of this methodology, you can decipher exactly where that is happening. For example, over here, you can see that out of the core bound, you're spending most of your time in your divider, right? There are a lot of mechanisms, even doing left shifts and stuff, where we can figure out, instruction level optimizations to improve the same. I can see that there's some questions.
I was going to read it out. So David Ozog asked, are the edge weights in the map you show average latencies, or is it cumulative, or could it be either depending on the application?
Not depending on the application, but it can be either. What I have shown over here are cumulative, but because this information is collected dynamically at runtime, all that data is in maps, which can then be converted into averages, and even more importantly, into P99 latencies, which are very important in the microservices.
That makes sense, and I think I'm just wrapping my head around this map step, and it need not be latencies, right? I think you mentioned it could be like, data transfer sizes, or
that's correct.
Even bandwidth throughput or something like that.
Yeah. Yes, that's correct. So in this example, we took the start point and the end point over the TCP lifeline, and we figured out, hey, this much time is being spent. The same can be done for how much data is being transferred, or same can be done for data transfer divided by the number of the bytes and the packet size, and you could find bandwidth. So sure. Yes.
Sure. Interesting. Yeah. Thank you.
Thank you. Okay. Going back to this, the data from this can be useful for understanding the application characteristic and in essence create a signature of your workload, right? You can say my workload is so much front-end bound, or my workload is so much back-end bound, or is there a scope for optimization or not? Some of this work can be used for noisy neighbor analysis, right? Where multiple applications that land on multiple instances or nodes can have a lot of front-end boundedness. Some can be extremely cache sensitive. You wouldn't want to put all cache sensitive applications onto the same threads or onto the same processor, right? So having this characterization map lets you learn about what does my application leave an imprint or a footprint on the processor, and how I can leverage that. Now, let's say we have identified in the last step that characterization has generated the data, and we have found out, hey, my application is extremely cache sensitive, or my application has got a ton of branch mispredicts or misses because it is just every few instructions I'm having a branch, and my compiler hasn't done a good job of predicting the right branches, right? So once we have identified what that problem area is, now we want to go to that step, which generally we like to jump into, is where in code is this happening? And there are a lot of different methods that can be done, but typically it is a time-based, and as I've given an example of perf here, it is a time-based approach where we try to figure out where are my cycles being accumulated. However, one has to also think that only looking at cycles alone may not be the most optimal way. Yes, cycles do tell us that where my time is being spent, but as we identified in the previous step, that I'm having a lot of branch mispredicts, which are causing me to have to go to lower levels of caches or have to go to memory to fetch data and come back. So the cycles are being spent in fetching that data, but the cause of it is actually a branch mispredict. So you really want to get to the cause. And because you have done characterization in the previous step, we actually know the cause, right? So imagine branch mispredicts are my problem here. You can do profiling, or you can do profiling in general with a specific metric like branch mispredict, or a specific metric like TLB miss, or a specific metric like cache miss at a particular level, right? That makes profiling even more effective, and that's the whole reason of why you would want to do characterization before profiling. Also, remember that characterization is a counting mode where the overheads are extremely low. We generally see overheads of less than 0.5% during characterization, because you're typically in a counting mode. You're only counting events. Whereas when you go to profiling, you're not only counting the event, but you're associating it with code. And that requires you to snapshot your instruction pointer, or and that makes it a high overhead operation. So software profiling generally has overheads, and the overheads are dependent on what you're profiling, how frequently you're sampling, things like that. So branch mispredicts or L3 misses per instruction, we can generate profiles on each. The flame graphs, as many folks might know, is a very popular and intuitive method of creating a visual of what the profile looks like. And below is just an example of how you can create. There are hundreds of options with perf, but given a very simple way of profiling. So let's look at one of the profile. I collected a profile on something that was running. I think it was Kafka running here. And while it was running, we can do profiling at different levels, right? Profiling can be done, or flame graphs can be generated on CPU cycles, which means when actual CPU cycles are being executed. It can also be done during off CPU cycles, which means when my CPU is idle, what is happening? What's the kernel doing? You can combine these. Then you can do system level profiling, which is what is done here with perf's -a flag, or you can apply it to a PID. And perf will basically trail only that process, right? So you'll only be collecting data from that process, and you wouldn't know what's happening on the rest of the system, which is fine if we know that our process is the issue. And typically, you would do this with CPU cycles, but as I said, the perf command can be twisted to say, hey, do not just collect on CPU cycles, which is default, but with the -e flag, I'm telling you to collect it on branch mispredicts, or I'm asking you to collect it on L3 misses, right? And or on page faults, metrics in the OS, such as context switches or page faults. And you would see that a flame graph such as this would be generated which is a very simple visual, but lets you, quickly dive into two things. One is how much time is being spent in a particular module or function, which is denoted by the width over here. And secondly, the stack itself, like who's calling who, right? So here, and it also allows you, because it dumps in an HTML format, it allows very easy search mechanisms. So as an example, you can actually go, and I went and searched for SSL because I wanted to see how much time was being spent in crypto over here. And you can see it accumulates all the places where SSL has been called, and it gives you, it's not shown over here, but in the window, you'll see that it accumulates it to say 40%. So we quickly figured out, hey, when I was running Kafka, where is most of my time being spent? And 40% of the time was in doing cryptography. Okay. So now that we have described the major aspects of the 7 steps, one, the map, and then filling it out with the 2 major Zoom methodologies of characterization and profiling. Now let's get to the third one, which is even more deeper than profiling. So now we are not only looking at an entire stack or a profile or just time being spent, but now we are getting into down to the either the code level instructions, or we are getting into the hardware level instruction tracing, right? We are exactly finding over a timeline what are the events that are happening. Now tracing can be done at various levels, and it has its own overheads, right? Tracing is usually done for debug. It provides you a timeline of events. It can be done statically or dynamically. Typically, I'll give an example of Jaeger, which Doshi was initially referring to, and that's where you go in and put your instrumentation into code. Now that, let's say, we know that we had done profiling, we figured out within Kafka, let's say cryptography was the place where I want to profile, know why it's spending time, what's exactly executing. I could go into those functions, put my hooks in, and then rerun the workload, right? Now, all of that could be done, but then it does pose higher overheads because a trace collects a lot of information over time, but it allows you to tell, hey, A executed, then B started executing, C simultaneously executed, or C called D, or D cannot execute unless C is done, typically in a function call, things like that. But all of this can be made better. And today with eBPF, you can basically do dynamic tracing without having to do that code insertion, right? Let's say I know that an SSL function with a function name is executing. From my previous step of profiling, I can introduce dynamic probes. I can actually get all that data, and with the help of eBPF, do in-kernel filtering to dump out, only the requested information. So let's say I did perf, and perf dumps a huge amount of data, or the trace amounts, but I'm interested only in certain sections of that trace. Then it's not necessary to do all that kernel to user data transitions that typical tracing tools would do. But you can only say, hey, I only want to know certain part, or I only want to know what were the parameters passed, right, within that trace. And you can do this in a very low overhead and secure manner with the help of eBPF. As an example, the component breakdown step, in which David asked the question about what is being instrumented, that was built on an eBPF tool that looks at the network stack. It essentially instruments the TCP stack and quickly looks at what were the latencies, what were the packet sizes, things like that. And it does dynamically. You don't need to touch code, right? This can be done in a production environment securely at any time. So, okay. So now that we have gone through characterization, profiling, and tracing, which is as deep generally you can get into with perf methodologies. Now let's find out the next 2 steps out of the step, which are related to finding out what might my bottlenecks be, or is my application scaling? Now growth is going to be inevitable, right? As we intelligently manage all these resource allocation, identify prospective bottlenecks, we are going to face more traffic. We are going to, as we add software optimizations, we are going to see that processors do better. The software in general is going to evolve, is going to handle more transaction. But dynamically, as this happens, let's say we made a software change, we made our branch mispredicts better. Suddenly, you'll see an insurgence of a lot more traffic, or you might see that your CPUs are utilized better. But what that does in effect is allows you to load them more. Now, when that happens, now a different part of your process, your application, the hardware might start experiencing bottlenecks. And these bottlenecks might be because of these parameter changes, such as a larger data set is being executed. Data is always growing. There are more users. You want more users as a company as you execute for generating more revenue. You will have more threads. You'll have more arithmetic intensity. And the general trend is, hey, I have more users. I have more. Let's just throw capacity at it, right? But just throwing hardware capacity may not always solve the problem, and we'll see why and how to figure out where your bottleneck might be. The figure on the right basically just shows, hey, this is known as a roofline analysis, where you would like to find out what are my maximas, right? And this is a memory cap for L1 cache, L2 cache, L3 cache. There's a cap for CPU. Imagine you can do the similar kind of analysis for network and storage as well, and know as you scale up what these caps look like. Now initially we were saying there are these scaling bottlenecks. Now let's look at what can be done to answer those questions about those bottlenecks. So scaling measurements, as we call it, is an excellent way of figuring out what those bottlenecks are, and it's also easy to search for those limits that we talk about and whether we are encountering those. Now, an application, as it scales, there may be parts of the application. Let's say there are certain parts of the application where the thread parallelism is pretty awesome, and we get all the threads used in the system, and we are getting maximum out of it. But there may be parts of the application that are sequential, or that are prone to locking, or prone to synchronization. It's inevitable, right? But some of them might be necessary and some of them may be unnecessary. And you might encounter scaling issues in those parts. So being able to identify what part of an application is running into those scaling bottlenecks is important. So sensitivity analysis will uncloak whether a reason that a service or a microservice or a collection of them are failing to get certain hardware resources, or failing to reach to their maximum potential. Right, that can be done by sweeping across core counts or sweeping across frequency, and I'll explain what that means in the next chart even further. But also things can be done with thread concurrency scaling, right? So imagine that you have a few threads and you can actually keep scaling the number of thread until the system runs out of resources. But you want to know which resource are you running out of and when, right? So to be able to identify these bottlenecks. And these could be, as I said, due to synchronization or very typical memory allocation and freeing even, right? So let's take examples of a couple of these, right? Whenever you do scaling experiments, the number one rule is you want to be changing one variable at a time. You don't want to be changing a number of variables. So for example, you take an application, doesn't matter what it is, and you change the frequency of the CPU across it, right? It goes from 1.8 to 2.4 gigahertz, let's say, and the throughput scales. You can establish an equation with the help of this, right? Similarly, you fix the frequency, you don't let other things change, and you let the core scaling, right? You change the number of cores on the platform that the application is running on. Now, you will typically find that sometimes you would see a nice linear curve, sometimes it immediately drops down. But with the help of going beyond the requirements of what you typically run at, you'll be able to identify these very easily. Core scaling can be done via BIOSes, via Linux core offlining, with the attention to its topologies. It can, frequency scaling can be done with frequency drivers by setting, thresholds on turbo MSRs and things like that. But once these curves have been established, what we have done in the past is we have taken an application, generated these equations, and created a model of the application. Now, what that helps with is in the future, if we were to predict software changes or hardware changes on newer architectures, we can reuse this model to establish, hey, what would my application behavior look like if I change this or if I change that? Right. David, let me know how I'm doing on time. But
yeah, you're 11 minutes left.
Okay, thank you. So with the help of identifying non-scaling parts, here is a quick example. Thread concurrency on the x-axis, what you see in this chart is thread concurrency. On the y-axis, you see performance of some application. Let's, doesn't matter what. It is a multi-threaded application though, and as we scale the number of threads, you see, oh, performance is going great and it's increasing, but there is a limit after which it suddenly stops dropping down. And what was found out was, after the scaling experiment was done, that there was fault sharing, right? As Doshi had pointed out earlier, fault sharing is nothing but, you've got different threads accessing, let's imagine the declared variables that fall along the same structure or a cache line, as we call it, which is 64 bytes. When different threads are going to access these data structures, read and write to them, which have no bearing on each other, like this thread 0 talking to variable A, which is in red, and thread 1 talking to variable B, which is in blue, have nothing to do with each other. But the underlying cache line or the 64-byte data structure is the same. Every time I change the value of A in this cache line, it's going to be invalidated in the CPU1 because I have to maintain consistency, right? And when CPU1 asks for that data structure, it's going to ask Mr. CPU0, have you been done with it? Can I take that data structure and modify it for myself? And then there is this ping pong between these CPUs. And there is more overhead of keeping consistency than actually accessing data and using it. That's essentially fault sharing, right? And that's been identified with by these non-scaling parts. Let's move on to auto optimization. Now, we've done all this process of performance characterization, component breakdowns, software profiling, identify. Now, how can we automate all of this? Even though most users run, most of the users will be running out-of-the-box configuration, right? Those hardly ever give you best performance. And even if we do one optimization in one service, it's not necessary that the same applies elsewhere. On top of that, there can be, the whole process requires a deep expertise in hardware, software, as we were going through these, right? There are a lot of resources, and they can be very expensive resources. And the whole effort of this process, imagine this was being shown on one application. If we were to continually do this iteratively on a microservice, there's a lot of manual effort involved, right? So this is an attempt to be able to put all this into a way of automating it. Not everything can be, but this shows a very good method of automation, which is really required for a complex beast like microservices. So with microservices being a complex solution, that so many variables can impact it, and there can be so many permutation and combinations, right, within each service that can impact the overall throughput or latency or your KPI. We would want to be able to take care of all these interdependencies and still be looking at a holistic performance of that microservice. One way of doing that is, imagine this is a proof of concept tool from Intel, where you'll see on the left-hand side, you see all the knobs that can affect the microservice. Let's imagine they are workload configurations, such as a Java service. Let's take Kafka, right? We are running Kafka. It's a Java knob. You've got hundreds and hundreds of Java knobs being a Java service. You've got operating system configurations. You've got hardware configurations that we talked about, that we saw with the health check tool. Now, imagine if we were to change one configuration, what's the impact to performance? And imagine if we were to change many of these knobs in different permutations, then what would be the impact to one microservice or a cluster of microservices? So the tool has something called as an executor that executes these, runs the workload, and in effect, it gathers all that performance data in terms of system information, telemetry, and gets that data stream, runs it, and provides feedback to what happened when certain knobs change, and then provides intelligently a machine learning algorithm that allows it to change another knob. And eventually, and way quickly than what a person would be able to do, figures out that what the best combination of those is for that microservice, right? So the optimization, again, iteratively keeps running that loop. I'm going to skip over this slide, but feel free to connect with us on this particular tool if required. These are the results of some of these. Getting, spec JBB is something that's been running for years, and we have optimized it for years, right? And we know squeezing even 1% out of it takes many months in and manual hours. With this service, we were able to squeeze out over 13%, and mind you, in a fraction amount of time, in less than a week, in few days, right? So that shows the power of automation on top of all the performance methodologies. I'm not going to walk in through all results in interest of time, but I'm going to move to security, because with today's digital transformation and evolution of cloud computing, there is a need for a rock solid security against these data breaches. And in microservices, where distributed networks and storage are most evident, you'd see security needs to be ingrained horizontally across every component, right? But with security and all that communication chatter that you're trying to secure with encryption, and let's say memory encryption or encryption, network encryption or encryption at the storage, whether data is at rest or moving, now you're incurring a lot more performance overheads because you're increasing the amount of encryption at every point over here. So as an example, here are some overheads that we measured on PHP WordPress. We ran it with HTTP and we ran it with TLS version 1.2 and 1.3, and you can see there's almost 20 and 30% performance drops as we move across higher encryption standards. Now, this has to be made a consideration. This was just a monolith. Imagine this in a microservices framework. We are likely going to see higher overheads, right? This was just SSL termination. You would have other overheads coming from storage and so forth. So hardware also introduces, right? Modern architectures provide a lot of mechanisms for securing data, and because it is in hardware, it eliminates a lot of these overheads, right? On newer Intel processors, you'd see something like software extensions, memory encryption, symmetric and asymmetric crypto, and hashing, which cover for a lot of this performance. So the graph that we saw in the previous chart, we recover a lot of this cost when we move it. We move the same software stack, but by using the hardware instruction sets that are provided. This is another example of taking advantage of acceleration that is present within the hardware. What the red line signifies is a baseline with an older generation processor, which was in 2019. And in 2021, the newer processors enabled crypto, which has been in JDK 17 and ported up to JDK 11. And all these encryption algorithms like AES, SHA, you can see there's multiple increase, right? There's 2x up to 5x increase in some of these by utilizing the hardware acceleration. So wrapping up, microservices architectures are bringing in a lot of moving parts, right? And performance becomes paramount. There's a lot of analysis, optimization that needs to be thought of. And performance, what was in the monolith, now becomes much more convoluted, as we saw, as does its analysis. So not just optimization, but auto optimization also is very important to bring in its part. And performance analysis it requires not only looking at what we have today, but looking into the future through things like scaling measurements, and through things like paying attention to the non-scaling part of applications, like we saw, being able to understand what resources are being utilized, what resources are under stress today, and where we need to put our software or hardware effort into tomorrow. There's an immense need for new tools and methods, right? The older ways of looking at things, their overheads just cannot be tolerated in today's world. And we need newer tools to be drilling into, as we saw with certain examples over here, whether it's a single or chain of microservices. And like I said earlier, automation is something we need to incorporate, because it's almost impossible to be able to, individual performance issues can be solved, but to be able to do this recurrently over time, and to gather and to gain the performance in places that one may not even think of, automation can play a very, very important role. So with that, I think that's the wrap up. Thank you very much, Doshi. Is there anything you would like to add?
No questions, but you might want to flash the other slides, the backup slides.
Okay. So this is the slide for resources. When we distribute the slides, I think you'll have access to many of these things here. If there's anything else you'd like to talk about, feel free to connect with us, Doshi or myself. Our email IDs have been presented at the title of this presentation, as well as some glossary terms over here. And with that, I think, David, we're done, unless there are any questions.
I think so too. Yeah, thanks very much. I think that's just a fascinating talk, especially since I'm actually ramping up pretty well in microservices, and juxtaposing it with HPC is interesting. I have a side conversation with Manju, just even simple things like frame. I don't think flame graphs are really used in HPC, is sort of one example.
I see.
And we're trying to figure out why. I mean, it's just a Linux profiling tool / way of viewing a profile, right? But anyhow, I think it's it's a little unfortunate there are no questions in Slack, but I think that's also effective, it being a tough time slot, the last talk of the day, last talk of the week on a Friday.
Yeah.
Yes.
Yes, isn't it? Yeah.
Just to add to David, I think it's a really good talk. Myself coming from a HPC background, right? I think it's really good. And also, I think for HPC, we need to tie everything together and look at scale all together. That is one of the tricky problems, right? So maybe
yeah. And with HPC, one assumes you're working with high amounts of parallelism, so you may not encounter, but I'm sure there is low hanging fruit with the help of.
No, in reality, we do encounter.
Yeah, that's what
we don't want to encounter, but we do.
Yeah, and I think, in HPC in practice, it's very, very rare to see any sort of software architecture that even resembles anything like a microservice application, right? But I think that you do see HPC, scientific workflows, which I think very much reflect some of the problems that you see with microservices, and especially, sort of the problem of having a plethora of tools, but also, perhaps difficulty in correlating, some of the behaviors you're seeing, or like I think Doshi was saying earlier, something I thought was really interesting, that loosely coupling microservice components is a good thing, but in some sense, maybe paradoxically, it kind of tightly couples profiling tool phenomena. I don't know if I said that right, but that makes
performance effects get tightly coupled.
Yeah, I see that as maybe being a hurdle in HPC as well. And I do see, I think HPC, at least, in industry, is already starting to move to the cloud, and examples are like AWS's parallel cluster. And, we know everything. False sharing is something we deal with all the time in HPC. But when you say like SSL takes 20% of our workloads, that doesn't happen in HPC. They don't care. But it might, sort of behind the scenes in something like a AWS parallel cluster, because I'm sure that's all on top of, at least something like SSL or TLS,
Right.
without users even knowing it. But yeah, I think there's certainly more discussions to be had here. And yeah, thanks for participating in our experiment to incorporate a completely new topic in the Hot Interconnects tutorials.
Definitely. Thanks for the opportunity, David.
Yeah, thank you all for the wonderful opportunity you've given us.
Yeah, thank you very much. And yeah, that wraps it up. So have a good weekend, everyone.
Have a good weekend. Bye.
Have a good weekend.
Bye now.
Thanks.
Bye.